we already explained some spray combustion system for spray burning. And here I just want to show you some pictures to let you uh, have a more understanding on real structures for applications. Here, the first one I want to introduce the gas turbine used for the aircraft. Okay, there is the two pictures. You can see clearly the structure of the gas turbine combustor. The upper the upper figure show you actually the main components for gas turbine in for the aircraft. Basically, they will contains in front of the whole gas turbine will be the fan, and they use it to suck the outer air, the cool air into your turbines, and they will go through the compressor to increase their pressure. Then they will go to the combustion chamber here. After the burning, those hot products will move to the downstream to make the turbine working. And later on, because they will spend certain energy to support the rotating energy for the turbine, and those turbine will connect to the former combustor. Actually, they have the same the same axis they connect together. Okay, and later on those energies still have in the high temperature product, they will go through the nozzle injecting out, and this is the whole mechanism you may have. Let me explain the sequence for the flow for the gas flow movement by this the loader part. Okay, the first one, air entrance, enter from the fan. Okay, then they will be increased the pressure later on by the compressor, and then the pressure is increased, and the flow will flow into the combustion chamber. There is the several combustors arranged surrounds the whole the gas turbines, and there is the drive shaft connect the turbine here with the compressor. As you learn the so-called the Brayton cycle in thermodynamics, you understand there is some work produced by turbine, but those kinds of work is just sufficient to drive the compressor to increase the pressure of air. And those kinds of connection basically just like we transfer the work from the turbine to the upstream compressor, and we'll still have a lot of thermal energy left. They will go through with the high temperature products to the downstream side. In the downstream side, they will go through the so-called nozzle to increase the velocity of your products. In this sense, that means by energy conservation, the kinetic energy of your mixtures, high temperature products increase, then that means that you need to lower down the total enthalpy for the mixture they contain. Therefore, those kinds of increase kinetic energy will convert, and to let you know the flow velocity will be increased by large velocity injection out from the nozzle. That means that you will produce the thrust to push your turbine moving forward. Okay, because the hot product will injecting out to the downstream side, and the thrust will produce those thrusts will push your turbine to move forward. And this is so-called jet propulsion theory. Okay, and this is a mechanism you can figure out. There is a combustor. Later on, I will give you a more detailed description. Actually, we already explained it from our lecture slides. Okay, and additionally, I want to tell you in many applications, especially for the so-called firefighter, since when you look at the structure for the gas turbine, the energy released by the spray burning, the fuel spray burning, those heat of combustion will convert certain amount of those heat of combustion to the work of the turbine, but most of them will convert to the kinetic energy of the exhaust gas and try to increase the velocity of your injection mixtures and produce the thrust to push your gas turbine moving forward. And you understand, if you look at the, the, the suction of air into your whole gas turbines, as you remember, we will split the airstream into the so-called primary air and secondary air. Primary air will go into the the combustors to complete combustion. But there is a secondary air. They will move along the annual the annual part annual port, and a certain they will flow into the combustor by the liner and try to cooling down the surface of your combustor, and later on they will move to the downstream. Actually, those air we already apply certain amount of energy to increase their pressure, but they do not to participate the combustion process. That means in the downstream side, in the downstream sections, the mixture contains certain amount of fresh air without burning, right? Then you still have oxygen left in the downstream side. Now, those oxygen can be used additionally by so-called afterburner for the firefighter. Firefighter usually they join the battle and they try to attacked the other plane. When they attack the planes, the other aircraft, they need to escape very fast. When they try to escape, they need to have an instant sufficient power to increase the thrust to let the firefighter be accelerated and moving out from the battle region. Then there is the chance to increase a large amount of energy to push your aircraft to move out from that region. Then the application is like this. They will have additional so-called afterburner after the exhaust of your gas turbines. Okay, here you can see this is the arrangement for afterburner. They will supply the fuel. You remember, as I mentioned, you remember in this the downstream of the exhaust hot gas, actually they contain still a certain amount of oxygen without participating in the combustion process in the combustion chamber of the gas turbine. Therefore, you can use those oxygen for additional burning. Now you have oxygen, but you need to supply additional fuel, right? Now here for the afterburner, you have another fuel supply line. Here you can supply the liquid fuel into the several small burner, and those burner arrangement will provide the burning in the downstream of your nozzle. Then they will produce. They have some combustion behavior exists, and then they will release a certain amount of heat of combustion. Then after that, they have additional energy coming out, and those energy burnt gases will move out of the afterburner. Then they will provide additional thrust to push your aircraft has some acceleration. This is a typical arrangement for the afterburner. You can see there is the several afterburner arranged in connect together, and those kinds of burning in the afterburner I already explained for the premix burning. As you remember, I show you this some kinds of experiment apparatus we studied very earlier, and this is a typical small scale of afterburner for the air for the firefighter. You can see there is the fan for swirling for apply the swirling to the flow and enhance the mixing. And here in the upstream side, in the upstream of the afterburner, there is some fuel supply. You can imagine. In this case, the experiment was performed by the propane fuel. But in many aircraft, they use the liquid fuel as the for injecting in to produce the spray frame. And there is a V-gutter, as I mentioned, because the flow velocity is very fast. Then you need to have some blood bodies to stop to produce a certain region, flow region with the lower velocity, and the lower velocity is good for stabilization of the terminal premise frame. And here is the V-gutter used for stabilization or frame stabilization. And I mentioned previously, this is actually this is another good experiment because the frame is already flashback to the upstream side. Then the hot products, the hot temperature gases flow through the afterburner and hitting the afterburner. Then you can see the structure of the afterburner. Actually, the color show you the reddish and yellow color represent, and this afterburner made by steel is already hit to a certain high temperature. Okay, in real burning structure should be observed in the lower pictures. You can see there is the blue flame stabilized in the downstream of your afterburner, and also in the in back also stabilized in behind of the V-gutter. Okay, and then those is different kinds of burning structure. Actually, we increase the supply of the propellant, then the flame becomes more you become more rich, then you can produce the yellow flame. This is a typical experiment for the burning in the afterburner. Then you go back to see the older structures for gas turbine used for the aircraft. You can see this is the mainly you can have a spray combustion in the combustion chamber, and then later on you will have a spray flame in the afterburner. For the afterburner, you can see they should have a very intense burning exists in this region. Then you can you wish to have a more efficient premixings together. Then usually the spray atomization will occur in before they reach into the afterburner, and we will have a more related to the gaseous combustion behavior in the afterburner. Okay, then we call this the spray systems in the afterburner system. Actually, they're more related to the spray atomization, and for the flames exist in the afterburner. Actually, they do not have too many droplets exist. They are more purely more modeled by the gaseous flame, gaseous turbulent flame, premise flame even. Okay. And now we move to the gas turbine, stationary gas turbine for electricity generations. And you can see these figures actually tell you still have the same structure. They have a compressor in the upstream side. Then they have several combustor arranged in this product. You can see there's at least 4 to 5 or 6 combustor in this arrangement. And later on, you can see there is several stage for turbine. Okay, and after that, they will you can see there is several. Actually, for the stationary gas turbine, they have a more stage because they have they just deliver certain work, a certain power to drive the compressor in upstream, but the rest of most of the energy output will drive the electricity generator. Okay, but the most important thing is I want to mention for the stationary gas turbine, since they burn the gas fuel, and they burn the gas fuel or light fuel oil, then you need to have some arrangement for the prevention on thermal knocks, because for the gas turbine combustor, you need to have a good mixing and then therefore the spray atomization always has an optimal situation to produce so many tiny droplets. That means the gasification and the mixing go to the optimal situation. In this situation, then the burning is very strong, and temperature will increase to a high level, higher than the threshold for temperature threshold for the thermal NOx formation. Therefore, some designs to prevent those kinds of enhancement on thermal NOx is required for the gas turbine combustion. Here, I tell you, okay, this is a basic structure. These two figures are very similar, and this figure they tell the supply of fuel actually coming from the beginning. Here there is a fuel spray nozzle, okay, but the upper one here the fuel supply from the periphery and maybe at the center portion of the combustor, okay. And you understand the air will coming in accompanied with the fuel injections, then the burning will occur in this combustion chamber. Similar way, you can figure out the combustion exists here, but this figure will tell you how the combustion process proceeds depends on the flow field you may have in the combustion chamber. Here, let's look at the flow structures. The position one tell you the primary air coming in. Actually, this configuration corresponding to the pictures shown in the upper side. Okay, now a primary air coming in. Okay, and here they will try to have some flow design to make a recirculation zone. A pair of recirculation zone exists in the combustion chamber, and the fuel supply from the side part, because there is a fuel supply, there's the position 4 fuel supply in, and when you have a fuel supply, those kind of mixing will occur in the recirculation zone, and this recirculation zone try to give you the optimal mixing for the liquid fuel, the liquid droplets, and also with the air, and they will continuously move to the downstream side. Here in the position 3 in this region, they will complete the combustion. And by this kind of recirculation zone designs, you can have a good mixing. And this is the first advantage. The second advantage, you try to arrange all the thermal output, thermal release to a large area, and try to reduce the temperature lower than temperature threshold for the thermal NOx. This is so-called NOx formation preventation. Okay, and later on those kinds of products will mix together. Finally, there is some air. As I mentioned earlier, there is the so-called secondary air. They move around the ends of the combustor, and they flow into the combustion chamber and mix with the products together, then go to the downstream, okay, to push the turbine rotate, and later on they will generate electricity, okay. And those kinds of design on the recirculation of your airflow with the liquid fuel basically is a good design. Try to prevent the thermal NOx formation. And here there is another application for liquid rocket engine. And these figures tell you the typical liquid rocket engines. And the liquid rocket engine mainly compose several sections, 1 to 6. The first one, actually, because we are talking about liquid rocket engine, that means the fuel is the liquid, and also oxidizer is liquid. Okay, and then you will have two chamber for the liquid fuel, the number one, and the other one for liquid oxidizer. And both of them will be driven by the pump. There is at this section 3, there is two pumps separate carry the fuel and the oxygen into the number 4, the combustion chamber. Here that means that now the spray system contains two kinds of spray. One is the fuel spray, and the other one is the oxidizer spray. Okay, they will mix together here and finish the combustion, then later on the heat the hub exhaust will be choked and at the throat and impinging out to produce the thrust, and those thrusts will push your liquid rocket engine liquid rocket to move forward. Okay, and now I try to give you some understanding about the mixing of the liquid fuel and the liquid oxidizer by atomization and produce the later the burning. Okay, and you can see there is the typical configuration to let you know fuel and the oxides they were supplied to the pump separately, and those pump will provide the pressure on the liquid fuel and also the liquid oxidizer to make a good atomization. Actually, those kinds of atomization will has a certain design, several different kinds of design I will explain in the later for different figures. And then they will finish the spray combustion in this region. Then later on they will move. They will produce the hot gas and exhaust out. Okay. Basically, as I mentioned earlier from the lecture notes, for the liquid rocket engine, actually those spray atomization, they try to produce the well atomized and mixed together where even they are still in the droplet situation. For example, you have fuel droplet, you have oxidizer droplet, but they try to mix well, and therefore the combustion structures is more related to the so-called premise spray frame. Okay, it's a complete different with the so-called the spray diffusion frame. And how to make a good mixing for the liquid rocket engine? There's several types. The first one we say the doublet impinge. Actually, those kinds of injector relate to the so-called train fluid injectors. Train fluid injector, that means that you have two kinds of fluid, then they will interact together to produce a good atomization. For the first case, doublet impingement, that means that you will have several couple of liquid injections together, the fuel supply from the fuel lines and the oxidizer from the other oxidizer supply line, but they were supplied to the individual injectors. For example, here fuel supplied to these injectors, okay, and the oxidizer were supplied to this injector. But we try to arrange the impingement coming out for the fuel and the oxidizer. They were just hit together at certain point here, okay. Now then you have a fuel coming out, you have oxidizer coming out. Then the next point you still have oxidizer and a fuel. Oh, and there is the fuel and the oxides. Okay, then they impinge together by two jets. One is the fuel, the other one is the oxidizer. And by this impingement, the trim fluid injections, then they will produce well mixings of the fuel droplets and also the oxidizer droplet. Later on, they will they will proceed spray premise burning in this region. Okay, this is so-called a doublet impinge stream pattern. There is another one we call this triplet impinging stream pattern. That means that at the impinging point, you allow three different kinds of liquids that interact each other. The arrangement is something like that. There is the oxidizer supply and the fuel supply, oxidizer supply, and the fuel supply. And we look at for this as a case, there are fuel coming from the center, okay, and there is the two oxidizer coming from the other sides, and three liquids that impinging together and produce a very efficient interaction and mixing. This is the impingement point. Then since at this point we have three different kinds of liquid stream that meet together, then we call this as a so-called triplet impinging stream pattern. And the third one is a self-impingement. Self-impingement means the liquid fuel impinged by themselves with two strings. Okay, here there is the fuel nozzle, the other one is the oxidizer nozzle, and they are separated in the arrangements. And for a given fuel injectors, they will go through the two ports and inject two liquid streams, two fuel streams that meet together. And for this case, actually, we call this a cell impingement instead of the pre to be has some distinguishment comparing with the previous two. Previous two always have a string of air, a string of oxidizer, and the other string will be the fuel that impinging together. But for this one, the impingement caused by the string, basically they belong to the same for the same liquid fuel or oxides. They will impinge by the two hole injecting out together. And the final one is the shoulder head. I think this is a very you can figure out because in but there is a shoulder head when you in your washroom when you understand there is a design for the shoulder, and they will provide the stream of the water coming from the top, right, and just straightly they impinging out, and this is a shoulder head string pattern just like this for fuel and the oxidizer. They just impinge uh, parallelly for different liquid streams for fuel and oxidizer, and they will have a breakup of the liquids of the fuel and oxidizer. Then therefore you can see one stream of the fuel, one stream of the oxidizer, then they are separate and easily to meet together to have a good mixing. Later on you will have a very nice premise spray bonding. Okay, this is a typical structures for the spray atomization in a liquid rocket engine. By this kinds of arrangement, actually the good atomization and the good mixing with the liquid fuel and the liquid atomizer is the main purpose. Therefore, when you have this kinds of good atomization, good mixing, for the later combustion process, they were more related. I'm sorry, to the spread premise bonding. Now, this is a typical example for the spread diffusion flame you may have for the industrial furnace. Actually, this industrial furnace is a smaller one. Combustion chamber, the length of combustion chamber is not too long. And by observation on this burning structure, actually they mentioned they give you, maybe you can see there is the very strong axial momentum injecting out. Therefore, the flame will extend to a longer distance without any change of the flame shape in this region. Actually, the influence of the natural combustion is relatively weak for this combustion chamber. But generally, you can see this typical spray diffusion flame, and the spray coming out, okay, and burn with the air surrounds it, and they show you the diffusion shape, okay, the yellowish spray flames. And the final one I want to mention is the ignition and also combustion of the diesel fuel in the gasoline in the diesel engine. And this is an experiment for the diesel engine with the quartz plate. Since the quartz plate, you can see the combustion injection, the spray atomization characteristic, and continuous combustion process. And this is a good, very nice experiment to let you know the detailed structures for spray atomization and burning for diesel spray. Here, let's look at the series pictures from the top. There is the so-called -10. -10, actually, they tell you this is the angle, the crank angle of your diesel engine. When the angle equal to the angle equal to 0 means your piston is moving to the top dead center. That means that the maximum movement, okay, is the top dead center. And later, when you move to the top dead center, the later on they will move back. Okay, when they move to the top dead center, that means the piston push the air inside a cylinder to increase its pressure. Okay, but usually for the real application in diesel engines, the piston movement, the injection usually occurs earlier than the top dead center. Here the experiment tell you -10, that means before the top dead center, the spray jet already impinging out. Okay, this is the initiation of the spray impingement. Okay, now when you have a spray impingement, there is the even in this case, you can figure out the diesel spray is impinging out under high pressure. Then they produce the solid cone sprays. That means that they can impinge to a further a larger distance. At the end of the spray here, you can see they have some kinds of extension of the spray region. That means that you will have more tiny droplets, diesel droplet exists in the tail of the spray. At this moment, the next moment, you can see ignition occur. You can see this is the ignition start. Okay, in this region, droplet size is small and have a strong mixing with the high temperature air. Then the ignition will be started by this high temperature environment. The chemical reaction proceeds. And in this, as you ignite the spray, actually the spray coming out continuously, right? More diesel fuel will coming into the combustion chamber. Then the combustion region will be expanded, not just the radially direction, then also they move to the actual directions to the more downstream region close the end of the combustion chamber. Then the combustion of your diesel droplets is continuously. Then you can see those kinds of combustion extend to the whole combustion chamber. And typically pictures to tell you, for example, for the spread the critical angle around 20, you can see there is the more dark region occurs. That means in this region you will have more fuel concentrate in this region, and those kinds of products also produced in this region. Later on, this dark region will extend from the right hand side and expand to the left hand side, and all the combustion chamber contains the high temperature products. And now the pressure is increased, and they will push your piston move downward. Actually, those kinds of combustion process, spray combustion process, occurs accompanied with the motion, the movement of your piston. Okay. And this is a so-called single jet diesel combustion. But in many applications, you try to enhance the mixing and also the burning in a short time interval for diesel engine operation. Then people try to introduce the swirling effect, because the swirling will enhance the mixing of your liquid droplet with the air. And this is in the right hand side. This the series picture tell you now you have 4 injectors, and this is pictures from the top of coach from top coach windows. You can see there is the 4 injectors injecting out at the -7 critical angle. Actually, before the top dead center, they injecting out, and later on they will ignite very easily. But this frame is quite different with the previous one, right? The previous one is only single jet without swirling, then they just impinge out directly into the combustion chamber. But here, like you can see, the flame generates here, the spray coming out, but flame has some motion accompanied with the swirling directions. Okay, and those kinds of swirling motion effectively increase the mixing of the combustion products, also the fresh air and liquid diesel droplets. Then the combustion intensity, a combustion process will be promoted. Okay, near the top dead centers, actually the spray flame ball, they almost cover a certain area, at least 1/3 and or half the total combustion chamber. Later on, the flame expand to the surface, to the boundary of your cylinder. Finally, the whole color will change it to yellowish, yellow color, and also more dark region occurs. That means that they finish the whole chemical reaction, and the air and the diesel fuel reacts to convert to the products. Okay, and from this two series pictures to show you the spray burnings in the diesel spray. Actually, they were the spray burning behavior, uh, even the spray atomization behavior, they were accompanied with the time variation and also the position. Therefore, when you try to analyze the diesel spray burning, you need to consider the coordinates and also the time change. And it is relatively difficult to simulate the diesel spray burning because you need to consider the transient effect.